So now that we understand some of the experimental and theoretical underpinnings of electron spin, we're going to be looking today at effective interactions between spins. Our goal here is to show how ordered spin states like ferromagnets, where spin imbalance, spin polarization, and equilibrium arise, especially in the solid state. We'll first review the symmetry constraint on the two-particle fermion wave function and see how spin degrees of freedom are coupled through electrostatic interactions. And then we'll look at a generic Hamiltonian where this so-called exchange interaction is relevant, leading up to a quasi-infinite system of coupled spins as a model for a ferromagnet. As you've heard in Professor Golitsky's earlier lectures, a system of two indistinguishable particles must yield the same measurement of electron probability distribution regardless of how the two sets of quantum numbers apply, to the first and then the second, or vice versa. This means that particle exchange implies the acquisition of a unit amplitude complex phase, and two distinct phases we see most often in nature are 0 and pi, giving an overall coefficient of +1 or -1. These correspond to bosons and fermions with integer or half-integer spin, respectively. Electrons are spin 1/2 fermions, and so acquire the negative spin upon particle permutation. For a two-electron system, a convenient normalized real space wave function satisfying this constraint is given here. Switching coordinates r1 and r2 is the same as multiplying times -1. However, there's more to the electron's degrees of freedom than just its coordinates. The total wave function is the product of the spatial wave function with a spin wave function, constructed from up and down single particle states. The spatially antisymmetric wave function must therefore have a spin symmetric wave function, of which there are three possible orthogonal states having definite amounts of spin projections with the different values 1, 0, and -1. These three states are therefore called a spin triplet. If we have a spatially symmetric wave function, then the spin wave function must be antisymmetric. There's only one way to do this with definite total spin along the z-axis, a single state with 0 total spin. This is called the spin singlet. Note that for all these states, if one of the two spins is flipped, we necessarily change the spin wave function symmetry, and in turn must change the spatial permutation symmetry as well. Now the point we're going to make is that these two totally antisymmetric states with different spin and spatial symmetries have different energies. Let's take an example like the two-electron neutral helium atom. There's the usual electron nucleus attractive Coulomb interaction for each of the two electrons independently, but then there's the repulsive Coulomb between the electrons themselves, which involves both coordinates. Importantly, there are no explicit spin-spin interactions in the Hamiltonian. Now let's evaluate the energy associated with these wave functions of different symmetry. Note that the only difference here is the sign between the product states. Calculating the expectation value of the energy, the diagonal matrix elements of the Hamiltonian, gives us many terms. For instance, there are 4 terms related to integrals over the part of the Hamiltonian covering electron nucleus Coulomb interaction of the first electron, H1, 4 for the second electron, H2, and then the electron-electron repulsion term, H12. Since H1 and H2 terms are dependent on variables R1 and R2 exclusively, the cross terms in distributing the multiplication in the integrals vanish, for instance, in this one. Since H1 depends only on R1, the R2 integral can be done separately, but the wave functions are orthogonal, so the R2 integrals vanish. The same happens for the cross terms in the H2 integrals. However, H12 depends on both coordinates R1 and R2, so this procedure cannot be carried out, and the cross terms remain, along with the symmetric and antisymmetric plus and minus signs. These are known as exchange integrals, and we can write the energy of the wave function as the following. The plus is for the spatially symmetric and minus is for the spatially antisymmetric wave function. This exchange integral J splits the energies of two particle states that are distinct only by the spin configuration by an effective interaction due to the spatial and spin wave function total antisymmetry constraint. Now you might ask, why did we neglect direct spin-spin interaction terms in our Hamiltonian? The underlying electrostatic root of exchange energy between spins is far greater than any direct spin-spin interaction. This magnetostatic energy is due to one magnetic moment's Zeeman energy in the field of another, which we know from classical E&M, falls off as 1 over distance cubed. Using the characteristic values of Bohr magneton and Bohr radius, we find energy precisely the same as the interaction scale between the intrinsic electron spin and the orbital moment of an atomically bound electron. Evaluating, we once again find the fine structure scale, and despite a rest mass energy of mc squared of 500,000 electron volts, alpha, 1 over 137, to the 4th power is extremely small, and the net interaction of milli-electron volts is far smaller than the gross electronic energy scale of electron volts, where we can expect our exchange constant J to be. Even though the underlying mechanism relies more on spatial wave function symmetry, we can capture the net effect of spin exchange with a phenomenological Hamiltonian. Again, this is because flipping the relative spin orientation of electrons coupled electrostatically through their spatial charge distribution changes the spatial symmetry and induces enormous changes in energy due to exchange. This is the quantum mechanical version of dipole-to-dipole interaction, where we've replaced the usual vector dipoles with new ones having Pauli matrix coordinates. Clearly, from a classical viewpoint, if J is less than 0, this system favors ferromagnetism, since its lowest energy ground state occurs when the spins align and the dot product is positive. Now, how do we evaluate this Hamiltonian? There are spin up and spin down for each electron, so we expect exactly 2 times 2, 4 eigenstates. This means our finite-sized Hilbert space must grow from the 1 electron 2 by 2 Hamiltonian to a 4 by 4 Hamiltonian. We do this with the matrix direct product, which is carried out simply by multiplying the elements of the first matrix times the entire second matrix to form a block in the final result. The dot product between single particle 2 by 2 spin operators then takes this form, and upon substitution we see the need to perform straightforward multiplication of each term, then sum. This result is non-diagonal, but we know how to diagonalize it. This can even be done by hand. Here's the eigenvalues and associated eigenvectors obtained by diagonalizing the Hamiltonian. One with eigenvalue minus 3j, and 3 degenerate vectors with eigenvalue plus j. What are these states? Let's remember the correspondence between our 2-component single particle spin vectors and spin up and spin down. Assigning the first element to spin up and the lower element to spin down, we can carry out the direct product and see that the components of the 4-element state vectors define a basis of up-up, up-down, down-up, and down-down. Then it's clear to see that we have simply calculated the familiar singlet and triplet spin wave functions all over again. Now we may ask, what's the net effect of exchange in a system with a large number of spins on a lattice? This may be a model for a crystalline solid, for example. In general, our Hamiltonian sums over all possible spin-spin interactions, which is incredibly difficult to solve. To simplify this task, let's consider only short-range nearest neighbor interactions. For a given spin at the ith lattice site, we're only going to include interaction terms with the spin's 1 lattice constant along the crystal axis, so the exchange integrals are all equal. For a square lattice in 2 dimensions, that's just 4 neighbors, and in 3 dimensions it's 6. Now even this is a hard problem, but the form of the Hamiltonian suggests we make a further approximation, that all the nearest neighbors are identical. Then this Hamiltonian has the same form as a magnetic moment interacting with a fictitious exchange mean field. This mean field is what orients the spins parallel in a ferromagnetic insulator when the thermal energy is low enough for the system to be below a phase transition. But what about more common ferromagnets like iron, a metal? There the spins are not localized, but are more like free electrons distributed in space. Before describing ferromagnetic metals, let's review plain old metals. This can be thought of as a gas of non-interacting electrons with plane wave functions. The quantum numbers are just the wave vector components kx, ky, and kz. By applying energy minimization, we account for all electrons in the system by filling the lowest energy state at the origin in k-space, and then, remembering Pauli exclusion, fill in states ever farther, isotropically until every electron has filled a state. This creates the so-called Fermi sphere with a radius given by the Fermi wave number k sub f. But this picture does not capture the twofold spin degeneracy of every state with definite kx, ky, and kz. A better picture in this regard is to plot states not in three-dimensional k-space, but simply as a function of energy, determined by the square of the distance from the origin. Then we can plot states up to the Fermi energy, which have the maximum Fermi wave vector. However, as we move farther away from the origin in k-space, we construct a spherical shell that gets bigger and bigger and accounts for more electron states. The density of states, then, at a given energy is growing. Plotting the density of states as a function of energy reveals that for a parabolic dispersion relation that we have here for massive particles gives a square root of energy dependence, and it is of course the same for spin up and spin down. Now we can easily, but only partially, spin polarize this system by applying a magnetic field. Zeeman splitting the states spin up and down moving, while relaxation processes keep the Fermi energy constant in equilibrium. But in a system with ferromagnetic exchange, the mean field, which is far stronger than any terrestrial magnetic field, does this for us even in the absence of a real external magnetic field. The density of states at the Fermi energy is then asymmetric, and a spin polarization in equilibrium is maintained. Now, we might ask how we can make full use of these spin-polarized electrons in ferromagnets. For example, can we transfer this spin asymmetry to otherwise non-magnetic systems, either other metals or even semiconductors? And if we can, what are the processes that govern relaxation of that spin polarization back to equilibrium in the non-magnetic material? If those timescales are long enough, can we manipulate spin asymmetry before equilibrium is obtained? All of these questions are relevant to exploiting the spin degree of freedom in solid-state devices with the goal of addressing unique applications not effectively dealt with by ordinary electronics. This is the field of spin electronics, which has impacted us all through the development and use of the giant magnetoresistance effect in hard drive read-head sensors, the discovery of which was recognized in 2007 with a Nobel Prize. In the next lecture, I'll tell you a little bit about spin-polarized electron transport, especially the unique difficulties of spin injection and what you can learn once that challenge has been resolved.